Okay, why don't we go ahead and get started. Again, I want to welcome you from wherever you're joining us today to the IWCS webinar series. We have an excellent webinar for you today. It was one of the finest presentations that we had at our IWCS Cable and Connectivity Industry Forum a few months ago. So before we start today's webinar, my name is Dave Cadu, and I'm honored to be the CEO and Director of IWCS. I'll be your moderator today for our webinar. Just a few housekeeping items. I want to remind you that you are, as an attendee, part of a larger audience, and during the presentation, all the participants will be in listen-only mode. As also a reminder that this broadcast is being recorded for future viewing. We encourage you to submit questions, written questions, at any time during the presentation using the chat panel, which should be to the right of your screen on the webinar series virtual platform. So please type in your questions in that space and hit the send button. And your questions will be addressed, time permitting, at the end of the presentation. Again, try to submit questions in that chat box instead of the Zoom chat. If some of you are viewing the webinar in Zoom, please enter your questions in the Pathable virtual platform chat box. Our IWCS webinar series is sponsored by the Cable and Connectivity Industry Forum. Today, we welcome Dr. Yi Sun, Senior R&D Engineer and Distinguished Member of the Technical Staff at OFS Fitel in Georgia, USA. Yi will be presenting her paper on high-speed Ethernet transmission over multi-mode and single-mode multi-core fibers for Datacom applications. Dr. Yi Sun has a Bachelor's of Science and a Master's of Science in Astronomy from Peking University, an MS in Electrical Engineering, and a doctorate in Physics from Northwestern University. Dr. Sun joined Bell Laboratories in 2001 and currently is a senior R&D engineer and distinguished member of technical staff at OFS Fitel. Dr. Sun's research covers various novel optical fibers and their applications in Datacom and SDM. Dr. Sun is the holder of 12 patents and has authored more than 100 publications. Dr. Sun received several outstanding contribution awards from OFS, and in 2011, the Spirit Endeavor Award by TAG. Dr. Sun is a senior member of IEEE. So again, we welcome Dr. Sun. And if you want to see her paper, you can go to our archives and view papers 3-3 and 3-4. So, well, great.
Thank you, Dave, for your kind introduction, and thank IWCS for the invitation. Also thank Becky and Michelle, who's not here, for their support. Good morning, good afternoon, and good evening, depending on where you are. It's my pleasure to present high-speed Ethernet transmission over multimode and single-mode multi-core fibers for Datacom applications. First, I'd like to acknowledge all my colleagues and OFS multi-core fiber teams for their support and contributions. Also thank VRV Solutions and FIT Finisher for their kind assistance of hardwares. This outlines my talk. I use 3 slides in the background explaining the need for high density solutions, and the rest of my talk is about equally divided between reporting the high-speed Ethernet transmission over 8-core multimode multicore fiber and a 4-core single-mode multicore fiber. We conclude that it is feasible to support high-speed Ethernet transmission for datacom transmission using 8-core multimode multicore fiber and 4-core single-mode multicore fiber using today's IEEE standardized 400 gig Ethernet transceivers. Multimode optical fiber and single-mode optical fibers are physical medium for datacom transmission. These optimized multimode optical fibers support top of rack, middle rack, end of rack interconnects. 50-meter OM4 is specified for fiber to machine in IEEE 3dB short fiber reach task force specified proposed objectives. There are several IEEE standardized 400 gig single mode solutions for datacom transmissions. 400 gig DR4 is a parallel solution to support 500 meter interconnects, intra-DC interconnects. 400 gig FR4 and LR4 are duplex CW solutions, support transmission of in-campus building to building and a shorter range of inter-DC transmissions. The growth of switch bandwidth and capacity demand a high-density solution. We heard a lot about co-packaged optics recently. It brings the fiber to the chip to reduce power consumed by non-revenue generation network. There are both single mode and a multimode CPU proposed. The single mode CPU proposed is based on 400 gig base DR4 and FR4, and the multimode CPU proposed is based on 400 gig SR4 and VR4. For CPU, a larger number of fibers is integrated in a limited area, typically 150 by 150 millimeter around the switch ASIC. For example, using 400 DR4 for 102 terabits per second switch, but 1024 fibers using today's single core fiber cable will be needed. Another area for high density solution fiber cable is expensive duct for outside plant. Multicore fiber comprises several waveguiding cores in a single glass cladding. Thus, it promises density improvement by a factor equivalent to the number of cores in the same glass cladding. The value proposition for multicore fiber may apply to in-row switch to server applications, and also switch to switch, connect direct to the ASIC or onboard optics, or through a duplex LC connect the faceplate or directly to the pluggable transceiver. We developed the 8-core multimode multicore fiber and the 4-core single-mode multicore fiber to support intra-DC and the DCI transmission. Next, we'll share 800 gigabits per second Ethernet transmission over 8-core multimode multicore fiber. This is a cross image of the 8-core multimode multicore fiber. The 8 cores arranged circularly. Each has 26 micrometer diameter and 0.3 numerical aperture. The pitch is 41.6 micrometer. The glass OD is 165 micrometer. Fiber OD is 300 micrometer. This is the photo in the middle, the bottom middle, and schematic for the 8-core multimode multicore fiber assembly. The 8 OM4 fibers are combined and spliced to a short piece of a multicore fiber to form fan-in and fan-out assembly. The 8 OM4 fibers are terminated with FC connectors, and another end of the 8-4 fibers are taped down and combined to one fiber to splice to the multicore fiber. The multicore fiber section includes 2 pieces spliced together with the length about 1 to 5 meter. The end-to-end link attenuation from fan to fan-out is less than 5 dB. The crosstalk is less than -30 dB. The correspondence between the schematic and the photo is shown indicated by the yellow arrows. 400 gig base SR42 is one of the 2 PMDs SRD-PMD is standardized by IEEE 3CM standards. 400 gigabits SR4.2 converts 8 53 gig PAM4 electrical signals into 8 53 gig PAM4 optic signals. The medium dependent interface is a 12 fiber MPO interface. So 4 parallel stream of 53 gig PAM4 signals at a 50 and 910 nanometer transmits bidirectionally into 4 fibers. Another 4 fibers transmits another 4 parallel stream signals bidirectionally, and the middle 4 is unused. Instead of using 8 fibers, we can use 8 cores of 1 multicore fiber to carry the same capacity of signals. The 400 gigabits SR4.2 is built based on 100 gig BiDi building block. Since the 100 BiDi is a building block for the 400 SR4.2 in development for 400 gig SR4.2, a 100 gig BiDi setup with stress condition was used to assess the worst case scenario. We borrowed the setup and modified it to assess the crosstalk attenuation, stress eye closure penalty, and beta ratio for the 8-core multicore fiber. As shown in this figure, the 100 gig BiDi was driven by a FOIT 100 gig evaluation board. A scrambled signals, PAM4 signal at 53 gig is transmitted and detected by the evaluation board. A mode condition patch cord was placed after the transmitter to enlarge the mode power distribution in order to bring the encircle flux near the IEEE specification limit of 86% at 19 micrometer. Under that condition, is expected crosstalk attenuation, mode selection loss, stress eye closure penalty, and the source-related noise penalties will be more than typical VCSELs for typical commercial transceivers. So each core was tested individually, separately, one by one. This figure shows the attenuation measured using the setup just described. N is the test number, counting both the number of multicore fiber assemblies and the number of cores. Blue is 850 nanometer, green is 910 nanometer. The median value is 2.76, 2.79 dB for 850 and 910 nanometer under stress condition, respectively, and all values are below 5 dB. As comparison, we also measure the attenuation at 850 nanometer using a commercial 400 GSR8 with encircle flux near 99.7% and 90 micrometers. That's a very good one. And the median value is 0.74 dB, 2 dB is less than stress condition. This figure shows stress eye closure penalty using setup described. Blue is 850 nanometer and orange is 910 nanometer. So the median value is around 2 dB for both, and the worst case still 1.7 dB, better than the maximum specified 4.5 dB by IEEE 3 standards. It's expected crosstalk with VCSEL that has encircle flux near the specific limit will generate more crosstalk. This figure plots the crosstalk tested at 850 nanometer for one assembly, multicore assembly of 14 meter length, and 7 cores, optical cores, versus the input fan-in port number. All values are below -30 dB, and the scatter distribution is expected resulting from a very distance of 7 cores to the core carrying the signal. The stress eye closure penalty in previous slide is measured without taking the crosstalk impact counted. And to include the crosstalk impact, we run the transmission using 2 400 gig SR4.2 to the 40 meter of multicore fiber assembly inside of the box is a multicore fiber assembly. Here's a multicore fiber, 10 meter, and this fan in, fan out. The two 400 SR4.2 in QSFP-DD form factor was driven by a VRV 800 gig optical network tester. The two stream 400 gig signals were loaded to the 8-core fibers through to MPO and MPO breakout jumpers. So the total link length 18 meter, including the multicore fiber fan in, fan out OM4. The multiple connections included in the aggregate 800 gig signal were live transmitting the 8 cores. The bottom shows the spectral characteristics of the two 400 gig SR4 transceivers. This shows the screen capture of the receiver quality service for the two ports, port 1 for transceiver A and port 2 for transceiver B. That's after the transmission of the 18 meter hybrid OM4 and multicore fiber assembly. All layers were okay after more than 20 hours transmission, and we further evaluated the merging by adding added to the loss through a variable optical attenuator. 5.8 to 7.4 dB for added attenuation can be tolerated. That indicates the system stability. To extend the length, we use one 400 gig SR4 transceiver and then loop the signal, launch that signal to port A1 to A4, and then loop it back by connecting the 4 output ports to another 4 ports input of the multicore fiber, and then eventually receive it to port B5 to B8 and detected by the receiver. The total link length by looping back end up as 32 meters, and the bottom shows the signal flow, optical signal flow from transmitter to receiver for one channel. In the 910 nanometer and 850 nanometer, the 250 gig signals were transmitting bidirectionally. Here's the orange, that's 4 loopback jumpers connecting 4 output to 4 input to loop back. The error-free transmission was achieved over a long time. Post-FAC and pre-FAC 3.5 minus 7, 2 to 3 orders better than FEC threshold, and there's margins remaining. Attenuation end-to-end is 0.8 to 3.4 dB. Encouraged by 32 meter results, we investigate the maximum reach can be supported by this multicore fiber setup. And we end up loop the signals 3 times back to from one core to another core. Here's the to B1 to A6, and then B6 to B7, and then A7 to 88, yes. So end up, this resulting the total link of 60 meter, including 40 meter in multicore fiber, and 60 meter in the fan in, fan out, and then another 4 meters in the MPO jumpers. Here's a setup, photo of setup, and enlarged to show the 3 loopback jumpers, and there are multiple connections. And this is screen capture of the receiver quality service after 60 meters of transmission. No errors were detected after 2 hours, continuous transmission, 100% bandwidth were utilized. There's still some margins. Prefect BR ratio 5 minus 6. That's about 1 to 2 orders better than FEC threshold. And note there's crosstalk introduced, included as well, because other cores were also active transmitting signals. And this chart recaptures the 8-core FEC error statistics, 8-core multimode multicore fiber transmission. And here's the back-to-back. Here's 18 meter, and 32 meter, 60 meter. The red is the error symbols, correctable error symbols. From 7 to 15, there's no errors. There's no uncorrectable errors. And the prefect beta ratio up to 60 meter against phi minus 6, still orders better than the FE threshold, FEC margin 60%. And this figure shows the attenuation of 400 gig SR4.2 over the 8-core multicore fiber. Here's a 50 nanometer, and here's 910 nanometer, 18 meter, 32 meter, 60 meter, again 18 meter, 32 meter, and 60 meter. So it's less than 4.5 dB, even up to 60 meter. There are multiple connections and splices included in the link. And this recaptures the margin versus the link length for the transmission just shown. This is 18 meter, 32 meter, and 6 meter. The blue is for the 50 nanometer. Triangle, red triangle is 910 nanometer. So the margin decrease from the 18 meter to 6 meter, that's expected. But up to 60 meters, you see some margin. And there are multiple, up to 10 connections and 12 splices in the link. So this suggests the robustness and the stability of the system transmission, feasibility for system transmission supported by the multicore fiber using absolute standards 400 gig SR4.2 transceivers. And next, I'll share 400 gig Ethernet transmission over 4-core single mode multicore fiber. The image on the left is a cross image of the 4-core single mode multicore fiber. The 4 cores arranged circularly. Here's a mark. Each core meets ITU-T G657A1 specification. The pitch is 40 micrometer. Glass OD is 125 micrometer, same as conventional standard single mode fiber. That's very important. 125 micrometer glass OD allows the multicore fiber uses standard single mode fiber optical equipments. On the right is an image, a photo of fan out. Fan in same except the polarity for the 4 cores. At the bottom, schematic for the fan in, fan out. 4 single mode fibers combined and spliced to a short piece of multicore fiber to form a fan in, fan out assembly. The multicore fiber and the single mode fiber all terminated with SC connectors. 400 gigabits per second, 700 gigabits per second, potentially up to 1.6 terabits per second transmission were tested using IEEE standardized 400 gig DR4, LR4, FR4 transceivers over 5 kilometer or 10 kilometer multicore fiber. Here's a photo of the setup, and here's a schematic of the setup. Via the optical network tester loads the 400 gig signals from port 1 to 400 gig DR4, and then 4 stream for DR4 transmits to the 4 cores of a single mode multicore fiber through the fan in, and then detected at the receiver through the fan out. To assess the 400 FR4 and LR4 transmission over the 4-core single mode multicore fiber, we can disconnect the fan in, fan out for one DR4 channel and replace that with 400 FR4 and LR4 400 gig Ethernet traffic. That would end totally, resulting totally 700 gigabits per second aggregate signal in the 4-core fibers. Here's the spectral characteristics, 400 DR4, 400 FR4, and LR4 using the testing. The center wavelengths around 1312 for DR4, and from 1273 to 1330, 1333 for FR4, LR4 with span for 20 nanometer. This image captures the screenshot of a receiver quality service of the 400 gig DR4 after 9.73 kilometer multicore fiber transmission. Error-free resulted after transmission more than 19 hours, 100% utilization of bandwidth, no errors, no frame loss. And this table captures the FEC's error statistics of 400 gig DR4 transmission after 9.73 kilometer multicore fibers. Here's the back-to-back, and here's after 9.73 multicore fiber. The red again is correctable error, the FEC error symbols. From 4 to 15 number symbols, there's no correctable errors, and there's no uncorrectable errors. The prefect beta ratios slightly better, worse than the back-to-back, but at least 3 orders better than the FEC threshold. FEC margin is better than 80%. And this captures 400 gig FR4 after 5 kilometer single mode fiber transmission. And here's a 400 gig bandwidth, 400 gig signal with 100% bandwidth utilization and no errors. All layers are okay after 2 days, 18 hours transmission. And this is showing the 400 gig DR4 transmitting other 3 cores. That is to show the impact of crosstalk is included. So totally aggregate 700 gigabits per second, the live signals were transmitting through the fiber. And we checked the core one by one and summarize the receiver FEC error statistics in this table. Here's back-to-back, and here's core 1, 2, 3, 4 after 5 kilometer of transmission. And here's the error, correctable error symbols. From 5 to 15, no errors, uncorrectable errors. There's no uncorrectable errors. Prefect beta ratio is only slightly worse than the back-to-back, and still more than 2 orders better than the KP4 threshold. And also 2 to 3 dB for added loss can be tolerated by the system. And this screen capture for the receiver quality for the 400 gig LR4 after 10 kilometer for multicore fibers. So 100% utilization for 400 gigabits per second signals, the Ethernet traffic. More than 19 hours transmission, resulting no errors and no frame loss. And totally again, 700 gigabits per second aggregate signal were alive transmitting in the multicore fibers. And we checked the cores one by one, core 1, 2, 3, 4. And all, as shown by this table for FEC error statistics, there's from 4 to 15 no error symbols and no uncorrected error symbols, and the prefect beta ratios more than 4 orders magnitude better than the KP4 FEC threshold. So that indicates the capability of 4 by 1.6 terabits, supportable by the multicore fiber. Up to 10 kilometer for LR4 and 5 kilometer for the FR4. And this figure recaptures the prefect beta ratio. And here's 400 DR4, 400 FR4, 400 LR4, 400 DR4. This is back-to-back. And then with 5 kilometer multicore fiber, with 10 kilometer multicore fiber. And here's back-to-back for FR4. And then core 1, 2, 3, 4. 5 kilometer fiber, and the LR4 back-to-back 1, 2, 3, 4 for after 10 kilometer fiber. So they all orders better than the FEC threshold. We further investigate the robustness of the system supporting and the tolerance to multiple connections. So we use a 4 kilometer 4-core single fiber, and we unwrapped a couple hundred meters to lay freely on the floor to mimic a cable condition. We also looped the signals back from one core to another core to double the length from 4 kilometer to 8 kilometer. That also, not only the length is doubled, but also the number of connections. And for the 400 LR4, we loop back signal twice to extend the link to 12 kilometer and also triple the connections. Error-free transmission was achieved, and this summarized the prefect beta ratio for the setup just described. Here's 400 gig DR4 and 400 LR4. Here's back-to-back for the 400 DR4, and then 4 kilometer multicore fiber, 8 kilometer multicore fiber, And here's back for the LR4 and the 12 kilometer, 2 combination for different cores. And so prefect beta ratio 5e-7, and there's a margin 6.6 for 4 kilometers, 3.2 dB. For 8 kilometer can be tolerated by the system. And for 400 LR4, prefect between 1e-6, 1e-5, and 1.4 to 2.6 dB margin can be tolerated. So that's bring us to the conclusion. In conclusions, we demonstrate the feasibility and the robustness of transmitting 800 gigabits per second over 8-core multimode multicore fiber and 7 gigabits per second potential 1.6 terabit over 4-core single-mode multicore fiber using 400 gigabit Ethernet transceivers for reach typical for intra and inter-DC center applications. Thank you.
Well, thank you, Dr. Soon. Again, an excellent presentation and very good information and very useful, I'm sure, for our audience. At this time, we'll ask any questions that you have for Yi. Hopefully you've entered your questions in the chat box and we'll monitor that. So please feel free to enter your questions now. And Yi, one question that's come in, the most important basic technology for multi-core fiber use is how to fan in and fan out of each core in the fiber by reasonable costs to fit in data center equipment. Do you have any ideas for fan in and fan out?
You mean, do you mind repeat the question? You mean the cost of the, how to?
I think he's looking for just basically a how-to, you know, a technique or configuration.
Fan in, fan out to the, as shown in the presentation, you see both the multimode fiber, multimode multicore fiber and single mode multicore fiber has a fan in, fan out. The multicore fiber, multimode multicore fiber is integrated assembly with fan in, fan out. And the single mode multicore fiber has a separate fan in, fan out modules.
Okay, very good. How do you avoid bend loss in multi-core fiber?
I guess this question for both multimode and the single mode. For the multimode fiber, you see we have that in the wooden box, and the numerical patch was kind of 0.3, so larger than the conventional laser optimized fiber that all helps bending loss. For the single mode multicore fiber, each core meets the IEEE meets the RTU G657.A1 specification, the same as standard single mode fiber, the A1 single mode fiber, including the bending loss.
Yep. Okay, thank you. Do you avoid coupling between cores, or is some coupling required? Would this affect the cable design or the installation technique?
Not very sure what this looking for. I mean, using the fan in, fan out with proper polarity, the coupling at the fan in, fan out, you see the crosstalk, we characterize that or meter spec.
And does the cable is the cable design or installation affected?
For the multimode multicore fiber that is prototype is in the wooden box, not cabled. For the single mode multicore fiber, for the testing, I use the fiber on the spool. I would not expect much impact different from the single mode fiber on the cabling.
Okay, very good. What is the largest contributing parameter that affects the crosstalk?
Yeah, there are a lot of literature on this, generating like a pitch, and also the the core itself, and how far from the outer edge, those kind of things. I didn't design the fiber, I only ran the system testing.
Yeah,
so.
Very good. I'm not seeing any more questions. If you have any additional questions, please again type them in the chat box. We'll try and keep an eye on that. Becky will help me to do that, I'm sure. But let me go ahead and share the contact points for Dr. Soon. Again, we thank Dr. Soon for this great presentation. The paper will be both posted and archived on our website. This webinar will also be put on the website for rebroadcast, and you can watch it again. Here are the contact points if you wish to reach out to Dr. Soon. Each of the IWCS webinar series events are recorded and are archived, so you can look at all of the different webinars. You'll be able to see an index of them on our website. Normally it takes about a week or so for this webinar to be posted. The IWCS webinar series will conduct technical paper webinars in addition to other types of webinars from sponsored companies for spotlighting products and technologies. Our next scheduled technical paper presentation webinar event will be on Friday, January 21st in 2022. That is a mistake. I guess we have to start talking about 2022. But it will be at 10:30 a.m. Eastern USA time. That is typically the third Friday of every month. You can expect to see a technical paper presentation. So please feel free. You'll be receiving an announcement on the presentation that will be given, as well as a registration for that webinar. And please feel free to share the announcements with your colleagues so that they can join and register as well. Becky, do we see any final questions coming in?
Dave, I don't see any final questions.
Okay, very good. Well, it was, again, a very thorough and understandable presentation. So again, thank you, Yi. Before we conclude, let's certainly recognize and thank our IWCS partner sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, thank you to these leading suppliers in our industry for your support. For over 70 years, IWCS has produced the Cable and Connectivity Industry Forum and has been the recognized leader in showcasing new technologies in the cable and connectivity industry for products, processes, and applications. With perseverance and confidence, we are scheduling to produce our next 71st annual Cable and Connectivity Industry Forum to take place live in Providence, Rhode Island at the Rhode Island Convention Center. That will be on Monday through Thursday, October 10th through the 13th in 2022. I got that date right on this slide, so we'll get there eventually. And again, please watch your inbox, your social media, and our website to learn more as the information becomes available. Our IWCS website is iwcs.org. So again, thank you for participating today. We really appreciate it. And I want to wish you all very, very Merry Christmas, happy holidays, and a very healthy, happy, and fun new year in 2022. Look forward to seeing you and working with you again next year.